to be mindful of. So a typical one would be something like this. I've got z equals the cosine of xy. This is not hard, but I want to do two derivatives of this. And so this is where we get into a little bit of trouble because we sometimes forget the rules, okay? Now, regardless of which variable I'm taking the derivative with respect to, the other one would be treated as a coefficient at this point. So if I want the partial of z with respect to x, I see cosine of thing. And that's the language I use in my Calc 1 class. The derivative of cosine of thing is negative sine of thing times the derivative of thing. That's what the chain rule says. Now, what is the derivative of thing? Differentiating with respect to x, so what's the derivative of thing?
Y.
Y. Or is that, are you asking a question? No. Sorry. Does everybody agree with that? Because when I do this, it's the exact same thing, and then what? Times x. Piece of cake. But now I want the second order partials. Okay? So I now want to do the partial with respect to x a second time. Now this y is still a constant. Now since this y is treated as a constant, by the way, can I leave the y after? Do I have to move it? No. Do most of us want to move it? Yeah, but we move it for readability, not because it's a better answer, because we are treating it like a coefficient. Most of the time when you have polynomial-ish things, you rather them be in front of the transcendental function. Nobody writes e to the x times x to a power. You'd rather write x to a power times e to the x. It's easier to read and sometimes easier to manipulate, but it actually does not matter. Okay? So you don't have to do the rewrite here. So when I do this one, I still only have the one x. So I'm still differentiating this, but now what do I do with this y? So here's where, by the way, here's where it's not a bad idea. I'm going to show you why you might want to do this. If I put that y in front, now I'm treating it like a coefficient. So now the derivative of negative coefficient sine y would be what? Negative coefficient cos y, and then the chain rule factor would be y again. If I leave it in this form, that's correct, but a lot of us will look at the y and not be sure exactly what to do with it. Do you understand? You're seeing something there and you're going, is that a function? Is that... So one of the reasons why you might want to do this is it makes this a little easier, but now this is not a good final answer because I should combine them. So I think most of us would agree, yeah, that's the form this answer should take. Now having said that, x to the first power, y to the first power. Can you tell me what this one is? Look at the form of this derivative. Can you tell me both?
Negative x squared cosine xy.
Exactly. Every now and then you can be a little bit lazy. You see the exact same form, you see the same exponents. Now, could I have done that if either one of these had an exponent and they were not the same? No, there would have been no trick. But the fact is the form of this one and the form of this one should match. Beautiful. Now I want to do this is the one that's going to give us the most trouble in this case. I'm going to differentiate this one with respect to y, or I'm going to differentiate this one with respect to x. If this was a quiz, you should do them both. If this is an exam, you probably it's a time thing. It doesn't take a long time, but there's a couple of minutes there you go, you know what, I need to do something else. So sometimes you just have to trust the process. Okay? I say on quizzes, you can go into more depth and detail on your checks. You can do things different because you're not being timed. Okay? I gave a quiz yesterday or last day in linear algebra where people had to multiply or manipulate, determinants and multiply things. And I told people multiply it out and then take the determinant. And most people didn't. Problem was, I said if you make a mistake, then every single answer is wrong. And several people made a mistake, and therefore, every answer was wrong. And when you have a week to do a 2-minute problem, you probably should go all out. If you have a week to do this problem, you probably should do both. Why?
Check.
Yeah, it's an automatic check. If you get the same thing, there's no way you did it wrong. You can't get the same thing. independent of each other and be wrong. That's one of the reasons why you want to do the cross partial both directions, but in reality, do you need to? If you're doing it correctly, do you need to? No, but this is all brand new, so this is still kind of unexplored territory. So let's take this one and let's differentiate with respect to y. So now I say, okay, the derivative of the negative sign is what?
Negative y.
So it'd be, well, let's say it's negative cos xy times the chain rule factor of,
Y.
I'm differentiating with respect to y.
Oh, okay.
Now it's x. So right now I'm on, actually, you know what, I'm doing this, sorry. I said first, I said it backwards. Let me do this again. Let's do first, my bad. Times the derivative of the second, but with respect to y, that would be 1. Plus the second times the derivative of the first with respect to y. This is a better way to go. And then that would be negative cos xy times, here's where we get a little bit of trouble, times what? We're differentiating with respect to y now.
Thanks.
Now it's times x. Everybody got that? So first times derivative of second plus the second times derivative of first. Is there a pretty way to write this? Probably not. So minus, I will definitely put the xy in front. Okay? Now hopefully, when I do this one, I get the same answer. This one I had to use product rule because now I had two functions of y and I was differentiating with respect to y. That's the only time you're going to use product rule. There's a tendency that people want to use product rule when they don't need to. It's usually not the other way around. It's not usually we forget to use product rule, it's we often use it when we don't need to. And this is true particularly in Calc 1, when people are first learning the rules. I have people do this all the time. Something as simple as this. All right, I want you to differentiate, 4x squared. And so what do? Well, let's see, we have that's the first times the derivative of the second plus the second. Nope. If you get the right answer on this one, it's pure luck. This is not a product of functions. A coefficient, by definition, is not a function. Therefore, it is not subject to product rule, quotient rule, chain rule, or any other rule. It's a coefficient. And in fact, as an absolute rule, it is factored completely out of the derivative before you start the derivative. So if I'm doing this, it's 100% wrong. Now, but the derivative of 4 is 0, and you'd be correct, and you completely wasted your time. Do you know how often I actually see the 0 when people do it this way? Not very often. The fact that you saw it as a product of functions means you probably aren't going to see a 0. I'm probably going to see another 4. No, you don't ever use product rule on a coefficient because you don't have a product of functions. You have exactly one function. It's called 4x squared. Now, if I multiply that by e to the x or something, yeah, now I have a product of functions. So when I'm looking at this, is this a product of functions? Not with respect to x it isn't, but with respect to y it is. And there's where the partials can get a little bit iffy. That's why I wanted to go over that, just to remind us. Now, I want to go and do an application, and I love this application in Calc 1 because it's so simple to do and it's so powerful actually in the bigger picture. All right, let's go on our Wayback Machine. Let's go so far back in time that you may not have one of these. Wait a minute, what do you mean? Calculus without a calculator? Well, about the first 400 years of calculus, there weren't calculators, so yeah. People were able to do just fine in calculus without calculators. Now, processes could take a lot longer as a result, but there's still things. By the way, I'm having so fun. I have a class where I now have people who refuse to wear masks anymore to class, and I actually had to say yesterday, I have to kick you out of class if you're going to refuse to wear a mask. I go, this isn't an option. I go, this is an absolute mandate. I think, oh. But it's like every day now I have to go through this battle. Like, I don't want to wear a mask. I don't care. I don't want to wear a mask either. But it's an absolute requirement that you physically cannot be in any building on campus without a mask, period. If you try to walk into a doctor's office without a mask on, how far are you going to get? I know where my doctor's office is, they have a security guard right at the front door. He won't let you in. And if you try to do something, you're actually going to be arrested. It's ridiculous as that is. So I say, don't battle it. I'm still waiting. I think it's going to be any day. But I also said that all last semester too, by the way. I think it's going to be any day. that they're gonna say, we're done. And I'm going to be the first one to jump up and, I would do handstands except I can't, so, but I am so positive it's gonna happen soon. But it hasn't happened yet. Okay, here's what I wanna do. I want to estimate the square root of 16.1. I love using this example. Now, estimate is not the same thing as calculate or approximate. Estimate, and a lot of times we get confused, and I like to use this also as an intro to notation. Most people in math and science actually have incorrect notation and they don't know it because nobody ever showed them, told them, or enforced it, because 50 years ago, everything was legal because there was no technology, okay? How many went to high school, and you remember in your algebra books, in the back of the book it had tables of logs and tables of square roots? How many remember those things? Yeah, you looked up at every square root from 1 to 100, maybe 3 or 4 decimal places, or logarithms from 1 to 100. Why? Because these books were originally published long before calculators, so they had to be, the old-fashioned computers had to calculate these things. And they gave you terminating decimal approximations that were correct to all of these things. But then you had to use these numbers as if they were terminating decimals to calculate other things. What happens in general when you round things off and then you use them for future calculations? Do you get exact values later? No, in fact, as an absolute fact, the last decimal place of whatever you just reported is always going to be wrong. In fact, it could be right. Most people say it's a probability of 0.1, 1 in 10. It's actually more like 1 in 100. It's going to be wrong. So in science, what you say is if I need a 3 decimal place approximation, then always use 4 decimal place values along the way. That way I don't lose that last decimal place. But the problem is you gave decimal answers that you could not ensure were actually correct to all the decimals you reported. So they are not equals, absolutely not equals, because they're irrational numbers, but they're also not approximations. An approximation means that every decimal you reported, it was correct to that place, including proper roundoff. So you gave what were called estimations. You gave ballpark figures. You knew were very close, okay, for actually a few thousand years. What was the most common estimation of pi? I mean, you weren't around, I know, but I don't think your parents probably weren't around either. Does anybody know what was used for pi? In fact, a lot of people still use it for pi. It's because it's so convenient.
3.
You can do a little better.
3.14.
No, by the way, nobody in human history, I have fun with this. Nobody in human history ever used 3.14, ever for pi. Why? Because you only use 3.14 if you had a calculator. And if you had a calculator, you had a pi key. I'm talking about for centuries, for over 3,000 years, it was a fraction. Not equal, sorry, wrong symbol. Does anybody know? Come on. It's still in all of the algebra books. It will actually say use this for pi. 22 sevens. You guys never seen that one before? For 3,000 years, that's why humans being used as an estimation for pi, because they didn't have calculators and you had to multiply. So is that an equals? No, that's a squiggle. Squiggle means asymptotic. That's what squiggle means. Taylor series. Remember you used a polynomial instead of e to the x or instead of sine x or instead of cosine x. They weren't equal, but on the graph, right, when you're looking at them, did anybody have me for Calc 2? Remember we used to use Desmos all the time and I'd show you guys like a third or fourth degree polynomial. I'm like, my God, it looks exactly the same as my transcendental function for a while. So if I wanted to do a numerical calculation of my transcendental function, I could use the simple polynomial. That's why that's so powerful. Remember, pre-calculators. You could do this. Was it equal? No, but it could be absurdly close. Numerically, it's called an estimation. Graphically, it's called asymptotic. And what we're looking for is asymptotic convergence. I only get convergence when I take a limit as the number of terms approaches infinity. Yikes. You can do better. Excuse me. Try this one on your calculator. I have fun with this. I discovered this one on my own. I was proctoring an exam a few years ago and I forgot to bring paperwork with me and all I had was my titanium TI-89 for 2 hours. Oh my God, talk about painfully boring. So I just started messing around trying to find better fractions. I don't know that I've ever seen a better. This one agrees the first, I think, 6 decimal places of pi, by the way. So if you're going to use a fraction for pi, use this one. It's way, way better. But the point being, it's not equal to pi. It's an estimator of pi. So if I need a ballpark figure and I don't need the exact value. That's where estimations are good. Do we do estimations all the time? World population? Do we know the world population right now? No. So we say it's about, the population of the United States is about 340 million people. Wow, so it's actually 340,000,000 people? No. That's really a big round off. That would be a squiggle. You're going to take your car into the shop today. If they don't find anything else wrong with it, it's going to be about $200. Did they just write you up in equals? No. Did they write you up an approximation of your bill? No. What did they write you?
Estimation.
We call it an estimate, don't we? Oh. And then if they don't find anything else wrong, you get your bill, it's probably a value that's very close to that. Maybe it's a few bucks in either direction. That's a proper use of the term estimate. I'm giving you an estimate, a ballpark, circa. That's what all those mean the same thing numerically. So I want a value that's close to this. Well, obviously, most of us would say, well, 4 is a good starting point, except I want to do a little bit better than 4. Now, imagine there is no technology. So this is what we did in Calc 1. This is the very first application. So let's consider, first of all, the graph f of x equals the square root function. Okay, now, I know that point is on the graph. What I really like, I'm going to kind of blow this up a bit. I want this one here, 16.1. Problem is I don't have a calculator. I don't have the ability to do a calculator. But 4 is the square root of 16, and that's a really good starting point. So what we did in Calc 1 was we said, let's consider the tangent line at 16, 4. And if I consider the tangent line at 16, 4, then if I'm only moving 1/10 of the unit to the right, that tangent line is not leaving the curve very far. Do you agree? It's really close to the curve. Therefore, could I use the y value on the tangent line as a reasonable estimator of the y value on the curve? It cannot be equal. The tangent line left the curve. It's impossible to be equal. And certainly not an approximation. No, approximation is when I do 16.1 on my calculator. But it would be a reasonable estimator of the value. Agreed? So what I want to do then is blow up this picture right here, make it really large so we can see it. So if I blow up that picture right there, okay, so here is 16 comma square root of 16, 16 comma 4. So this would be 16.1 comma square root of 16. How's that? Now, this is right here, 16.1 comma square root of 16.1. I just blew up this. And this would be 16.1 comma whatever the y value on the tangent line is. But because we did the tangent line to a nice integer value, finding the y value on the tangent line will be trivial. It's a rational number. I don't need any form of technology. I can do that one in my head if I want to. We're going to go through that process. So the symbolic notation that we use is, this is the actual change in x on the curve. This is the actual change in y on the curve. On the tangent line, changes are called incremental, and we use a different notation. It's called, also we use the term differentials. And it's always a little bit confusing, and we use this notation to separate the two. On the tangent line, we say the change in x, we use dx. But in this case, it's the same thing, isn't it? The change in the tangent line and the change in the curve in the x direction are the same value. But they are most definitely not the same value in the y direction. So in the y direction, we call this dy. And here's the entire point of the problem. Delta y, we're going to estimate with dy. And really the rule of thumb is, as long as I don't leave the curve too far, then dy is a reasonable estimator of delta y. Now in my picture, they look really far apart. But in this picture, do they look really far apart? No, they're probably decimal close. Okay, that is the whole idea. So the question is, how do I get the dy? Well, let's go back to here then. To find the slope of a tangent line, I'm going to need the derivative of the function, aren't I? So what is f prime of x? 1 over 2 root x. Now, here's how we start. My starting point, which we'll always call x naught, is 16. 16, I have a formal term I use mathematically to describe 16. 16 will be called our happy point. And in 3D, we still have a happy point. It's the easy number to work with. 16.1 is not the happy point. 16 is the happy point. I'm asking you to do 16 plus a small change in x. So my small change in x clearly is 0.1. By the way, what if I had asked you to do 15.9? Then you would have used a negative value. Yeah, dx can be positive or negative. Which direction did you move? I had to move forward to get to that. Everybody agree with that? So whether I call it dx or delta x, it's the same value. Okay? Now, tangent line. Y minus the y value equals slope times x minus the x value. We've seen this formula before, right? Arguably the most commonly used formula in all of mathematics. And I said, seriously, I use this formula in Calc 1, 2, 3, linear algebra, and differential equations. I use it, and in fact, I use it multiple times in each of these courses. And it's not even a calculus formula, it's the point slope formula. It's so incredibly useful. So in this situation here, x naught would be the 16, y naught would be the f of 16, the 4. What would the m be? The derivative evaluated where? 16. At 16, at the happy point. Everybody agree with that? So let me rewrite this as y minus f of 16 equals f prime of 16, and then that would just simply be the dx. 16.1 minus 16. Oh, but then doesn't that make this dy? I mean, that's my old and my new. Oh, so dy is simply f prime of happy point dx. It's kind of a magic formula. This always applies in this context. So let's do it for this problem here. Okay, off to the side. F of 16, we all agree, is square root of 16, or 4. F prime of 16 is 1 over 2 times the square root of 16, which would be 1/8. Excuse me. Now, I don't need this anymore. So let me make you an absolute mathematical statement. In general, f of 16 plus my small change in x, and in this I'm going to use delta x, is equal to f of 16 plus the actual change in y. Look at this picture here. Okay? If I said, what is f of 16.1? Wouldn't it be f of 16 plus delta x? Or excuse me, delta y? Here's our problem. We don't know. We don't know what delta y is. That would require technology. But this is an absolute statement right here. So what do? We're going to estimate this with f of 16 plus dy. That's the whole point. This is absolutely correct. The square root of 16.1 is 4 plus whatever the actual change in y is. Of course, without a calculator, I cannot tell you what the actual change in y is. In fact, no human being could. That's beyond the limits of your brain. Some things you can do, calculating irrational numbers in decimal form is probably not a useful use of your gray matter. So this is what? F of 16 plus f prime of 16 dx. And what was dx in this case? 0.1. The actual change in x was 0.1. So let's put the numbers in. This would be 4 plus 1/8 times 0.1. That's the same as 1/80th, by the way. Or 4.0125. 1/8 would be 0.125. So, here's what I'm saying. The square root of 16.1 is equal to that number? No. It's being estimated by that number. So this would be the answer to the question using all of this stuff. Now, traditionally, would I have any way of knowing how good my answer was historically? No. But we have one of these. So can we check our answer? All right, let's check. What is the square root of 16.1? At least to 4 decimals, what is it? So on my calculator, the square root of 16.1, and this is where you use approximation. Means you're taking an irrational number, which has an infinite non-repeating decimal sequence, and you're reporting it to a finite number of places out of convenience. When you turn something in physics or chemistry, they don't really want to see you write every decimal on the screen, right? You have a graphing calculator, and the decimals just wrap around, right? You could probably put a couple hundred decimal places if you really wanted to. They probably don't want you to go more than a couple, right? It's kind of useless information. So if I said round this to 4 places, I got 4.0124, but it's 4/8, so that would be 5. Okay. So if I actually do the calculation of the square root of 16.1 to 4 decimal places, I got the same value. Huh. That means my estimation is pretty good. Do you agree it's pretty good? Now, what if I wanted to do 16.5, 17, 19, 25, 30? What's happening to my tangent line? It's getting further and further away. I can do this process for any number you give me. But what will the quality of my calculation be? Will it be better or worse over time, as I get further away?
Worse.
It gets worse. It's still an estimation, but it's not a very useful estimation because I can look at it visually and say, I'm getting too far away. I want you to estimate the square root of 99. Would you be using 16 as your happy point? What would you probably use?
100.
100. It's like, there's kind of an oh duh in there somewhere. Go, oh yeah, use something that's close to what you want. Now, this process in general was the very first application you do in Count 1. In every Count 1 book, it's the first application, and it's an estimation, not an equals or even an approximation. And at no point in this problem did I ever actually need technology. So let me state it now in the formal sense. There's actually a formula that is always true. Okay? I want to estimate f of x naught plus delta x. Assume x naught is the nice number, and delta x is the amount you change to get to the not so nice number. Okay? So it doesn't have to be square root. Heck, it could be e to the something. It could be sine. It could be anything you want it to be. F of x naught, assume, is easy. F of x naught plus delta x is the thing you can't do without a calculator. This is equal to f of x naught plus the actual change in y. And that is estimated by f of x naught plus dy. But dy, we just showed, is f prime of x naught dx. And that's the magic formula. That is true for every function that exists. That will always work. The quality of your answer, again, depends really how far did you move. So really the rule of thumb is how big is dx compared to what you're calculating. We use an x naught of 16. Do you agree that 0.1 is small relative to 16? Yeah. But what if I wanted to do the square root of 1.1? Now 0.1 versus 1, not quite so small, is it? It's getting closer together, so it's probably not going to be as good. Let's do another one of this nature, because we're going to do this in 3D in a moment, and you're going to see how similar it is. I don't have a calculator, and I want to estimate, how about 2.98 to the 5th power? Now, by the way, I don't have a calculator. Could I calculate that? Is it possible to calculate? Sure. Do you want to? You know how? Use multiplying 5 times. By the way, how many decimals does your final answer have? Does anybody know? This is one of those things you actually learned as little kids, but I guarantee you long since forgot it. The answer has exactly 10. How do you know? 2 times 5. You multiply a decimal value that has m places by a decimal value that has n, you get m plus n in your answer. So you just did 2, 2, 2, 2, 2. It's 10. I really don't want to do that by hand. I don't know about you guys, but I have better things to do. So let's use this. By the way, what would my happy point be here?
3.
3. And what would my function be?
X.
X to the 5th. I have to come up with a function because I have to have something that I can actually differentiate. That's why you have to define a function first, because I'm going to need a derivative of that thing at some point. Excuse me. All right. So f prime of x would be 5x to the 4th, and we all agree that x naught would be 3. What would my dx or delta x, and it doesn't matter which one you call it because they are the same. In the independent variable, this is an absolute, and it's going to be the same in 3D. For the independent variable, the change on the curve and the change on the tangent line are exactly the same. It's the dependent variable that they're going to be different. What's dx?
0.02.
Is it 0.02? Negative 0.2, because I'm going backwards. If I use a positive 0.02, then my answer will be an estimation of 3.02 to the 5th power, which will be way off, won't it? So that's why I'm doing one in the other direction, just to show you how simple the setup would be. All right, well, let's do some calculations. What is f of 3? That would be 3 to the 5th power.
243.
243. What's f prime of 3? That would be 5 times 3 to the 4th power.
405.
405. So formally the way we'd say it is we would say 2.98 to the 5th power is equal to 243 plus the actual change in y, of which I have no idea what that is. So I'm going to estimate that with 243 plus the incremental change. So now this is where I do my dy. And what's dy? It's the derivative times the incremental change. It's actually that simple. It almost seems, it's 0.2, almost seems cheating, but it's that easy. Yeah, I don't care how complicated the problem is, it's that easy to do estimations if you understand the process. So get out your calculator, tell me what this is. So you got 234.9. So I got a big long thing here. So what did I actually say? I like actually answering the question. The answer to the question is therefore 2.98 to the 5th power. We are estimating with 234.9. This is the actual answer. I think I did okay. Now I'll go ahead and check it by multiplying it out freehand, right? or maybe, okay. What is 2.98 raised to the 5th power? Actually, I'll put, it's actually 235.0072824. 282. I'm sorry, 28. I'm lost the place. 7, 2, 8. 2, 3, 9, 6, 8. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is exactly what it is. And your calculator was incapable of doing that. I have tricks that I know. Cheapest calculator on planet Earth. Maybe it gave me 7 decimal places. How do I get more? Well, first of all, subtract the 235, and now you get all of them. But what if it's got too many zeros in front, then multiply it by 10 or 100 or 1,000? In other words, you're preserving your numbers. That's the actual answer. My estimation is 234.9. The actual answer is almost exactly 235. Would you say our estimation is decent? But it's off by 0.1. But 0.1 compared to 235 is really small. That's another is a really good estimation, which leads us to our next thing. Relative error. The error is this difference. Is that a lot or a little? It's hard to say what is a lot or a little. Okay, so last week on the job, Kenny was off by 10 centimeters. He was doing his thing, he was off by 10 centimeters. Emily on her job last week was off by 20 centimeters. Sorry, Emily. Who had a better day? Oh, Emily, she's the crew chief of a construction project, and they were putting up a beam on the top of a building, and the beam was 400 meters long, and she had the end lined up, but the other end was off by 20 centimeters. She was so annoyed on a 400-meter beam. Kenny was performing open heart surgery and was off by 10 centimeters. By the way, about how big is a human heart? It's about 10 centimeters. So Kenny was off by the entire size of the heart. Sorry, Kenny, the patient didn't make it. His error was 10 centimeters, her error was 20 centimeters, but his relative error was 100%. Her relative error was, 1,000%. See, relative error is the error divided by what it's supposed to be. So if I just know the error, is that enough information? Not necessarily. So last week, also, Bowden was doing the books, and he was off by $5,000 when he was doing the books. Okay? Lena was doing the books, and she was off by $1 million. Yikes. Bowden has a little kiosk flower shop that does about $1,000 a week, and that $5,000 error costs you your whole business. Oh, Lena balances the federal budget, which is in the trillions. So her error was less than one millionth. A millionth squared is a trillion. Her error was less than a millionth. His error was 500%. You guys get the point? Relative error is a percent. The term relative always means percent, and a lot of folks get this confused. And I mentioned this, I think, before we talked about rates. A rate is any time you have a quotient of things that have units. So miles per hour, right? Dollars per gallon, price per pound. Percent is the same thing as a rate, except the units are the same. Oh, okay, I have to drive 100 miles. I've made it 50 miles so far, so it's 50 miles to 100 miles. That's 50% of the trip. A percentage is the same as a rate, except you have the same units. Rates, you have two different units. That's why you always give it as something per something. But a percent is unitless because the units always cancel. As an absolute, there's no exception to that. So you don't have a percentage with rates in it. That doesn't make any sense. So relative error is a percent error because it's something per something, and all your units canceled. So if I said, what is the relative error here? You take this difference and then divide it by this. Would that number be really, really small? Yeah, so you'd say my relative error is microscopic, and that's really how we judge the quality of an estimation. It's not how far I'm off, but how far I'm off relative. So the examples I just gave, hopefully it would make it kind of clear. It's not the amount you're off, it's the amount you're off divided by what it was supposed to be. And if what it's supposed to be is close to the amount you're off, then you have a huge relative error. And which would mean, in an estimation sense, it's not a very good estimator. In our first example that we did, our relative error would have been really, really, really small. Okay? This example is really, really, really small. So relative error is a fairly simple thing. Now let me do another one and before we move into 3D, because once we move into 3D, it's going to be all the same mathematics. It's actually really, really simple, but we have to understand it. So we make cubes. Cubes are us, okay? Cubes are us. I think we can do that because that toy store is out of business, so it's
Coming back.
Oh, okay. Cubes, there we go. How's that? I don't want to get sued here. Cubes are us. We make cubes. We make sugar cubes. We make those gigantic pods that you put in your driveway when you're going to move stuff, and a year later they're still in your driveway. And you guys know what I'm talking about? They've taken root and you can never get rid of them. I don't think I've ever seen anybody actually remove a pod once it made it there. But we make cubes of all sizes. So here's the thing. We make cubes, but it is possible that we can have errors in some of our dimensions. So let's keep it simple. Let's just say x, x, x. The volume of a cube is then just the dimension cubed. We make cubes, but let's say that any particular length can be off by as much as 1%. So let's say the max error in an edge is 1%. Is 1% a value? I just found this great savings account. I actually look for stuff like this all the time. And if you put your money in the bank, you're going to get $100 of interest every month. Wait a minute. Is there something wrong with that statement? How could I possibly tell you you're gonna get $100 in interest every month? So if I tell you that, just put a penny in. Wait a minute, that's not how it works. You don't get a dollar amount, what do you get?
Percentage.
A percentage of what?
How much is it?
How much you put in. Oh, you don't get dollar amounts, you get percentages of what you put in. You don't have any counts that give you a dollar amount per month. They give you a percentage of your, oh. So when I say 1% error, that's not a length, that's 1% of what it's supposed to be. Oh, so on a sugar cube, 1% would be really small, but on one of those big pods, 1% is probably fairly large, right? I can measure it, maybe it's a centimeter or two. So 1% of what it's supposed to be. That is key. So what we're going to say is that means in this case dx, we'll just assume we're going to have the maximum error, is 0.01 times x. If x is small, then dx is 1% of that. If x is large, dx is still 1% of that. Dx is not, I did not give you a value. Now, if I said every measurement is off by this many centimeters, then I've given you a value. I gave you a percent. Could I say this, then dx over x is at most 1%? Can I say that? By the way, does it matter if it's 1% too big or 1% too small? Does that matter? No. Anybody ever buy furniture from IKEA? I'm amazed, by the way. And there's, when you look to put it together, there's never instructions, is there? There's pictures. And then everything fits. But every now and then, you're trying to put something in the groove and it doesn't work. I mean, it's very, very rare. I've never had a bad experience, but every now and then something doesn't quite fit. There is something called a tolerance. Tolerance basically means the maximum percent error that you can have. And if it's too big, things won't line up and fit, or you're forcing things. But usually things just fit perfectly. But if the error is too large, it might not fit, and then you take it back and you get it replaced. Does it matter if it's too big or too small? No, it doesn't fit. It has nothing to do. I'm going to throw darts at the dartboard there. And I missed the bullseye by an inch. You don't say, well, yeah, but was it an inch to the left or an inch to the right? Was it an inch too high or an inch too low? I was off by an inch. Does it really matter what direction I was off? I missed by an inch. Direction is irrelevant, in other words. Anybody here ever work a cash register? Your job? Okay, I did when I was in high school. There's only one thing that ever matters in life when you're a cash register operator. At the end of the day,
There's enough cash in the...
No. You're at the end of the day when you're checking out, does it
What?
balance?
Oh.
Yeah. By the way, if it doesn't, you get fired. It doesn't matter if you have too much or too little. If that number is too big, you get fired. If you're short, by the way, it means, man, you're really bad at counting money and you lost the store money. If it's too much, you're stealing from the store and then you're fired and sometimes worse. How is it too much you're stealing? Because it means you are taking different dollar amounts and trying to keep it in. I've actually witnessed this. In other words, when the person was punching in the numbers, they were always one decimal place off. The $200 purchase only went in as 20. And then the person's paying the 200 and they're pocketing the other 180. But at the end of the day, it's really hard to keep track of that. So when the person at the end of the day has $200 extra in their cash register, they get searched and they find $1,000 in their pocket. By the way, just so you know what the big department stores, you know how you always have those big pillars everywhere with the glass? You know, the mirrors? You know what those are, don't you? Those are two-way mirrors. That's where security people, if you've ever been there right at the right time of day, you watch somebody walk out of one of those. People stay all day in there to watch. And they're not watching the customers always. Sometimes they're watching the employees because they have suspicions. I have seen on more than one occasion, especially during Christmas time, I've seen people arrested behind the counter during business. But that looks bad for that store because they saw the person had been stealing. Yeah, so your cash register operator, the only thing that matters, did you balance? And if anybody's like, you're off by a nickel, you're still mad, aren't you? You did $10,000 worth of business, but you're off by a nickel. Ugh. I don't want to be off. I want to be perfect. I want to be right on. So the whole point is, did you balance? Nobody cares in reality if we get too much or too little. Like the bullseye, you're off. You want to be right on. So when we're talking about maximum error, we don't care if it's too much or too little. It's just how much am I off, because things don't fit if you're off. So here's the question. If the maximum error in a measurement of the edge is as much as 1%, then what would the maximum error of the volume be? Huh. Now, I didn't give you a specific length, which actually makes the problem easier. If I gave you specific lengths, then you would have to calculate multiple things. But if I only give you percent error, it's actually an easier calculation, because now this will apply to all sizes. Numerical values would only apply to one specific size. So, if the volume is x cubed, then here's what I'm doing. First of all, delta V is being estimated by dV, and what is dV in this case? The derivative. What's the derivative?
3x squared.
3x squared times the incremental change. But I didn't give you an incremental change. No, I didn't. Okay, this is exactly what we just did. Do you agree? So therefore, maximum relative error is this. Delta V is the error in my volume. Delta V over V is the relative error in my volume. And this is now being estimated by dV over V, which is equal to what? You know, like this. 3x squared dx over x cubed. I didn't give you a specific size. No, I didn't. Because I'm saying for all cubes that we make. Now, does anything cancel? A lot cancels. Could I write it like this? So the estimation of my relative error in volume is this, but I still have unknowns. I still have variables. No, you don't. Where do we start the problem with? The maximum value of dx over x is 0.01. So what is this? I make cubes of every size imaginable. If the maximum error in an edge was 1%, then the maximum error in the volume would be estimated at 3%. Now here's why you like relative error. I didn't have to tell you how big my cube was. If I told you how big my cube was, then you have to do multiple calculations. But I only told you the percent error. So that made the calculation actually easier, didn't it? Everybody cool with that? So here's the thing. When I'm giving you a one-dimensional error and I'm asking for the maximum error, let's say the surface area or the maximum error in volume, it's never going to be the same number. That number blows up. So you could maybe live with that 1% per edge, but maybe 3% is too much. So this is where you have to kind of streamline things, change things around. Now let's look at 3D. How does all of this change in 3D? Well, it's actually almost the same. Now I'm going to give you, we're going to do this problem just like this, but I'm going to give you another glimpse of it in a week or so when we talk about tangent planes. Because I'm technically not going to use a tangent plane when I do this, but it really is a tangent plane. So we had a curve, we had a tangent line leaving the curve. Now imagine I have a surface, and I have a happy point, x naught, y naught, that gives me a happy z value. I want to move a little bit on the surface to an unhappy, icky x, icky y, icky z calculation. So if I have a tangent plane where the happy point is, now I move a little bit down the surface. Imagine I'm now moving on the tangent plane. And the z value on the tangent plane is what I'm going to use to estimate the z value on the surface. Does that make sense? It's exactly the same as we did with the curve, but now it's in 3D. So the process is very similar, although what we're not going to do today is actually calculate the tangent plane. That's later. That's, actually, I tell you exactly when that is. That's a couple days. The 5th, which is what? 1 week or 2 weeks?
1 week.
Oh, a week from today, we're going to do tangent planes. So, similar problem. Let's start with z as a function of x and y. By the way, the beautiful thing about what we're going to do, we can have many independent variables. We can have more. It can be bigger than 3D. And it's the format. It's the way we do things. Once you understand it in 3D, that process will apply no matter what dimension you're in, higher. Okay, so assume x naught, y naught is the happy point. Okay, this is the nice thing, but I want to do, you know, maybe that's 3 comma 4, but I want you to do now f of 3.05, you know, 4.02. And that might be really nasty to do that one. So we start with the happy point, and then the delta x and the delta y are how far I changed. This is equal to, like before, this plus the actual change in z, of which I don't know how to do because I don't have a calculator. But we're going pre-technology so that we understand the big picture. Okay? And I'm going to estimate that with dz. Now, what would dz have to be? Well, let's think about what we did here. In 2 dimensions, I only have one independent variable and one dependent variable. Well, you always have one dependent, but you only have one independent. And so what I did was dy was the derivative times the actual change. Well, guess what? dz is going to be the same thing. It's going to be the derivative with respect to x at x naught, y naught. Before we said f prime of x naught, because that was our only input. Now our input's x naught, y naught, times the actual change. Great. But isn't there also a y change? Yeah, plus. Derivative evaluated at happy point times incremental change. Derivative evaluated at happy point times incremental change. No, I'm using the fx. I could use the partial notation. Most of us like this. It's just easier to read. Am I saying the exact same thing here and here? Yeah, but now my happy point is an ordered pair. Oh, but then I got to do it for this. What if I had 3 independent variables? Then I add that one. What if I have 10? I add all of them up. That's it. This is exactly what we just did. We just have to do more than one. We have to do 2 of them because we have 2 independent variables. You're adding the incremental change for each of your independent variables. Okay? So let's do a really simple example of this. I'm going to use simple numbers here. All right? In fact, I don't need any of this. I want you to estimate, okay, so let's start with f of x, y, let's say is 2x cubed y to the 4th. I don't want this to be long and horrible. I want to estimate f of 2.02 comma 3.97. Okay? All right, y'all with me? Yes.
Just right there where you have f of fx times x.
No, evaluate
Is that
it.
the derivative though? Is that?
This is the partial with respect to x, evaluate it here. This is the partial with respect to y, evaluate it. Not multiply, evaluate it.
Yeah. Okay.
All right, evaluate it at. But why an ordered pair? Because now my input's 2-dimensional. Here my input's only 1-dimensional. So you're inputting the independent variables. Now, in the 3D case, dx and delta x are the same value. dy and delta y are the same value. dz is my estimate of delta z because that's the dependent variable. That's how it always works. You're estimating the dependent variable. You're not estimating the independent variables. So the change in 2 dimensions, the change in x on the tangent line and the change in x on the curve are the same. In 3D, the change in x and the change in y is the same for the surface as it is the tangent plane. It's the z change that's different that I'm estimating. So, what are we going to call our happy point? Oh, good lack of certainty. 2, 4. Yeah, 2, 4. Because those are the closest values. 2, 3 would work, but that would make my change in y way too big. 0.97 is really large when I compare it to the number 3. But 0.03 is really small when I compare it to the number 4. That's why this is a better choice. I want my change to be small. Okay? What is my dx?
0.02,
What is my dy?
negative 0.02.
Yeah, I did that on purpose. If it's negative, don't make it positive, okay? Because you'll be going in the wrong direction. I have almost everything I need. Now I have to take two derivatives this time. I have to take a partial with respect to x. I have to take a partial with respect to y. Let's do everything one step at a time. So what is the partial with respect to x?
6x, y, or 6x squared, plus and plus.
Now, immediately I'm going to say, and now let's evaluate that at the happy point. And go ahead and use a calculator for that. That's an integer value. I really want to get the right number here. Let's go ahead and calculate that derivative. This is what we did earlier. We calculated the derivative right away. Give me again number. You got a number? You don't trust it?
6,144.
Yeah, it's not a hard calculation. Now let's do the partial with respect to y.
Eight x cubed, y cubed.
8x cubed y cubed, therefore, the derivative evaluated at 2 comma 4 is
4,096.
4,096. There's still one more calculation we need to make. We have everything we need to calculate our dz now. What do we still need to do? That's the biggest number in the problem. We still need to actually calculate the function at happy point. Because remember, that's my starting point, and then I'm going to add the change to that. If I forget to do that, the only thing I've calculated is the change. But change from what? I need the big number first. So finally, we're done with all the calculus in the problem. The calculus was those two derivatives. So let's calculate what is f of 2 comma 4. So going back to the original function. You can do this first, you can do this last, just got to do it at some point. Also 4,096. Okay, so drum roll, please. F of 2.023.97 is equal to 4,096 plus the actual change in z. I don't have any idea what the actual change in z is. So I'm going to estimate that with 4,096 plus this times this plus this times this. Okay? So 6,144 times 0.02 plus 4,096 times negative 0.03. Now let's definitely get our calculators after this guy. Tell me when you have a value. Ooh. Oh, that's weird. Did you all get 4,096 again?
Yeah.
Well, we just proved it. For every question you could ever ask, the answer is clearly just 4,000. Well, okay, maybe not. Now, that's kind of funny. The changes kind of canceled each other out, it appears. Now, I'm pretty sure I did everything right, so let's move on to the next problem. Is there a check? There wasn't 50 years ago. There is now, because you got one of these. What's my check? Well, let's actually calculate this and see how close it is to our estimation. What if I was off by, I don't know, 100 or 10, 20? Whew, it's hard to know, but do you agree that 0.02 it's small relative to 2? It's 1/100th. This is small relative to 4. It's less than 1/100th. So I'm expecting error, but I'm not expecting error to be huge in this case. But it doesn't mean that you can only be off in decimal places. No, I can be off in the tens position. I can be off in the hundreds position. Our answer's over 4,000. If I was off by 10, that sounds like a lot, but 10 compared to 4,000 really isn't very much, is it? That's what I'm saying, it's relative error. So let's do this calculation. 2 times 2.02 cubed times 3.97 raised to the 4th. So the actual value is 4,094.926. It goes on for a while. Okay. My estimation is 4,096. This is almost 4,095. Would you say that's pretty close? Yeah, my error is barely over 1, and that's 1 over 4,096. So in terms of percent error, I actually can calculate. All I gotta do is take my calculator screen, subtract it from 4,096, or minus 4,096, and then divide it by my calculator screen. So my relative error is approximately negative 0.00026, which means I'm less than a percent. I'm
Absolute values.
roughly 2/100ths of a percent. I think I can live with that. My relative error is around 2/100ths of a percent. That's really small. So does that give you confidence in your answer? Yeah. Can your error be larger? Sure. When would I expect to see a larger error? I've already given you the idea. When can you expect a larger error?
When you have a larger change, larger deviations.
Or comparatively. So these numbers being large in general is probably not great. What if these were in the hundreds and these were larger but there were still decimals? We'd probably still say they were okay. Everybody okay with that? Notice, what if this was like 0.2 or 0.5 or even 1.3? That's huge. Not if these are in the thousands or millions. So again, think of it in terms of relative. They are very small in comparison. Relative, just think of it as a quotient. Oh, okay. Now, what's interesting is in real life, because this is actually real life mathematics, by the way, there's something I've used the term before called tolerance. Now, in any field, in any business, there's always a maximum tolerance. That's the acceptable error, it's called. When things are being made, even if it's made by a machine, is everything always perfect? Or can there still be errors? There still be flaws? The example I like using statistics, I have a bottling plant, and I fill bottles, tens of thousands a day. And I've set it, each machine, to how far the bottles are supposed to be filled. But if I actually looked at them, is it possible I see slight variations from bottle to bottle? The average is probably what it's supposed to be, but those variations, right, that's called the variance, that's the measure of consistency. The mean is the measure of the average. It's the consistency that's far more important. I can afford a little bit of error. But if there's a lot of error, then when you go to buy something, I am notorious when I'm buying stuff. I do my grocery shopping multiple times a week, and if I'm buying something with expiration dates, I automatically look in the back. I mean, everybody should do that. So the milk, the ones in front expire in 3 days, the one in the back expired in 16 days. I'm buying that one, right? There's certain things that everybody does. But let's suppose you're buying the potatoes. You're over at the grocery store and you're buying the 10-pound bag of potatoes. Yeah, I'll actually grab several bags and I will weigh them. Why? Because it's not possible to have a bag of potatoes weigh exactly 10 pounds unless you have a partial potato in one of those bags, which you never will. So one bag is 9.8 pounds, the next bag is 10.3 pounds. I'm buying the heaviest bag every time. That's what I do, right? Because there's going to be a tremendous amount of variation in this case. Variation is a measure of consistency. Mean is only the measure of the average. And in real life, nobody cares about the mean. It's always variance. You have entire courses that you study variance at the highest levels of mathematics and statistics. So I give the simplest example, right? When you go to buy that bag of potato chips and it says 14.6 ounces on it, and then you open it up and of course it's hello, 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 right? You go, and it says on the bag, some settling may occur, and you're going, I'm gonna weigh that bag, and it's not 14.6 ounces, it's less. By law, do you know that you have to be given your money back? There is no exception. The Department of Weights and Measures will come down so hard on the store that doesn't give your money back that the fine and the penalty isn't worth it. So if you're shorting customers, you actually have to replace it. If you go to a restaurant and they burn your food, you're going to ask for another meal. If you ordered that 16-ounce steak and you got this little tiny thing there, and you're going, no, I'm not paying for that. I ordered a 16-ounce steak. They have to make it right. They don't have a choice. They have to make it right. And if they refuse to make it right, you actually do not have to pay, period. So some people use that to their advantage. They complain about everything. They return everything. No, that's not what I'm talking about. So, then the fix is then always give too much. But then you're giving away product. If I give too little, I have to replace it. If I give too much, I'm giving it away. So in either case, I lose, don't I? I want no variation. I want everything to be exactly what it's supposed to be. Do you have complete control over that? No. That's why there is allowable error. It's called tolerance. Okay? Years ago, my father had a printed circuit board shop up in Santa Cruz County, and I ran the shipping and receiving department while I was going to school. And so I would drive into the Bay Area every single day and deliver. He made prototypes. So if you ever taken apart your electronics, your computer, you see a circuit board. Okay, that's when we made circuit boards. And you see all these little things, and you see all these holes that are got a little ring of copper or ring of gold around them. That's what they did. They made the circuit boards and they did all these things. But the quality assurance was a person with a gigantic magnifying glass going through every single detail of this, checking the tolerances, because the holes were drilled by hand. Why? Because they were making prototypes. They might make 4 boards. They made prototypes. There wasn't a pre-existing program to go ahead and cut it out. They made the prototypes. If the company liked the prototypes, then they sent the order to a big circuit board company who would then program the machine to drill everything exactly the same. But that program didn't exist when you're first building the board. So everything was done by hand, and there were certain allowable tolerances. The industry standard at that point was 0.1%. That was allowable error. And by the way, I'm sure most people still use something like that to this day. 0.1% is 1/1000th. That's acceptable in most everything, right? When I'm putting the furniture together, that's okay, things will still fit. But if it exceeds that, now you run the risk of things not fitting. So in the circuit boards, if you exceed that and those holes are not right, then when they're plugging in the little things, right, all the little things that have plugs, you guys have taken apart things, they won't fit, right? And so that's very, very important. So this is a way mathematically that we can measure stuff like that. Okay, everybody cool with that? All right, let's do an example where we're now doing something with the error, the percent error. All right, so before we made cubes, because in Calc 1, there's only 4 geometric shapes that you ever use. Circles, squares, spheres, and cubes. Why were those the only shapes you ever used? Because they're the only shapes that have one variable, right? A square and a cube has one variable. A circle and a sphere has radius, one variable. You didn't do circular cylinders because that has 2 variables. Not in Calc 1 and 2, but in Calc 3, oh yes. We can do boxes now. You know, boxes with different dimensions. Couldn't do those in Calc 1, but now we can do anything. Okay, because we can handle multiple. So, now we are cans are us. How's that? Not cubes are us anymore. So I have a can, right? That's the radius. That's the height. What's the volume? Remember? Circular cylinder. Same formula as a prism. Area of the base times the height. So it's pi r squared h. All right, we make cans. By the way, I'm giving you, this is real life. We make cans. The top of the can is soldered on to the rest, right? So the first part of the can is a rectangle that's now wrapped, and then we solder on, basically, you know, think of it like a melting glue of metal to put the top on. They're two completely independent things. So is it possible I could have either the radius or the height be off? Yeah, and if it's off by too much, it won't fit very well, will it? Plus, if it's off by too much, and I'm filling the things to maximize, again, it could be giving away stuff. I don't want to be doing that. I would really like my cans to be exactly right, but understanding when I'm making things, there's always a possibility there's error. So let's say the cans are supposed to be, the radius is supposed to, it's a pretty good sized can. So let's say the radius is, let's see. The radius, let's say, is 6 centimeters, and the height is, it's a big can, 15 centimeters. Okay, that's what it's supposed to be. The maximum error in the radius let's say is 0.1 centimeters, and the maximum error in the height is, let's say, 2 centimeters. I can calculate now what's the maximum error in the volume, what's the maximum error in the surface area. I'm more interested in the volume in this case. Now, I gave you the actual error. I didn't give you a percentage error. I gave you the actual numbers. I gave you what the radius is supposed to be. Now, is 0.1 relatively small compared to 6? Yeah. 0.2 compared to, not microscopic, but it's not huge. It's not a large percentage. So, let's find two things. The maximum error in volume and the maximum relative error in volume. These are separate calculations. Okay? Well, let's go back to here then. What is the volume supposed to be? I'll do it like this if you want. It's supposed to be what? That? And calculate. Let's calculate that. 540 pi centimeters cubed. This is very important that I get the units right, because if I don't get the units right, I may report the wrong thing. I may inadvertently be doing area when I meant volume, or I may be doing length when I meant area. So I always want to get the units right if there's units involved. Remember, relative error doesn't have units. Error does. So the volume is supposed to be 540 pi. I don't need to calculate the pi because the pi's are probably going to cancel later somehow or another. That's what it's supposed to be. Now, the maximum error, I don't care in which direction, it's how much I'm off. That's why someone used the term absolute value before. It really is absolute value. It's how much are you off by. It doesn't matter if it's high or low. And I talked about that when it comes to products in general, high or low is bad. Okay? I mean, what's worse, giving away product or having to replace something for free? Yeah. They're both bad, right? Replacing something for free is probably worse. Okay. So delta V, which will be estimated by dV, that means I have to take a derivative. Oh, but I have two different derivatives going on here. So, what is the derivative of V with respect, I'll write it out, R, then the derivative of V with respect to H times the incremental change. This is exactly what I'm finding. This is exactly what we did before. So, what is the partial with respect to R of V? With respect to R. 2 pi RH. And then times the incremental change, which we'll put in the numbers in a moment. Plus, now what is the partial of V with respect to H? pi r squared, good. And then dh. Now I'm just going to put the numbers in. We're done with the calculus for the rest of the problem. We took our derivatives. Now let's put the numbers in. Okay, so in our case here, dv is going to equal what? 2 pi times 6 times 15 times 0.1 plus pi times 6 squared times 0.2. So that's some number of pi's in this case. Do I have a number? I'll do my part. Something pi.
18 pi.
Well, that part will be 18. I still got that. Well, that's 18, so I think that we need a little more. Did you lose the 2? I think you lost the 2.
Yeah.
25.2.
25.2. Okay, so it's supposed to be 540 pi cubic centimeters, so this should also be cubic centimeters, shouldn't it? The maximum error in my volume, and by the way, what that means is if those are off by the most they could be off, is it possible that I have no error in reality? Is that possible that it came out right? Yeah, that's possible, but I'm not interested in the times it comes out right. I want to know what's the worst case scenario, because in reality, if the worst, let's go back to our bottling plant example. You know, I'm producing bottles and everything's fine, but when you go to the grocery store, you're never buying that, you know, that 6-pack where all the bottles are different sizes, or you're the one taking them out of one and putting them in the other and, you know, swapping them around. That one's not going to sell. Because you're looking at it going, no, this is garbage. I want the one that has some consistency. So I need to know how, in general, I need to know how far off are things in general. If my bottling plant is too inconsistent, that means I have to buy new machines. In real life, you replace equipment when the variance is too big. In other words, the lack of consistency. You know, you might not like things. I probably should. I don't like mentioning restaurants' names because they're being recorded. You all have restaurants you go to. You have particular extraterrestrial coffee shops that you like to go to, that, you know, or certain McRestaurants that you like to get your fries from. And one of the reasons you go there is not the quality. What is it? The consistency, exactly. You know what you're getting and it's exactly the same every time, am I right? That's why you go. Now, you're okay with the level of performance. Knowing it's going to be exactly the same is actually huge. If you've ever been to a restaurant and you love that restaurant and then they wreck your meal next time, all of a sudden you're like, okay, I might not be going back. Or well, last time I had a great meal, this time it was an okay meal, you know, I don't know what next time. You want the level of consistency. Great or not, you just want to know what to expect. And in real life, that's actually the more important measure. Not the quality, strangely. The quality is what the quality is. You're going to get what you pay for. So if you're going to a fast food restaurant, right? It's fast food. You're not expecting quality, but you do want it to be the same as it was last time. So that's the maximum error. This is the actual what it's supposed to be. So therefore, and here's the notation, the actual error over what it's supposed to be, this would be relative error. I cannot calculate, so I am estimating it with the incremental. This is what we just calculated, by the way. And it's very important to understand this cannot be equal. That's impossible. It can't, again, the idea I'm leaving the surface kind of thing. But the idea is it can be ridiculously close. So what is my answer? 25.2 pi centimeters cubed over 540 pi centimeters cubed Pi's cancel, centimeters cubed cancels. And now I should have a decimal value. Okay? And what do you come up with? I get, oops. Does anybody get something that looks like that? Yeah, you can write like that. So in words, it's 4 2/3 percent. My maximum error in the volume is exactly 4 2/3 percent. Now, by the way, I can't tell you what the answer is, but this is your company. Are you okay with that much error on a regular basis? You might say, no, I'm giving away. Do you realize what that does to your profit? If you're giving away 4 2/3, that means 4 2/3 percent of the profit. I'm giving away, or I'm shorting people as much as that, and I don't know if you would notice that. Maybe you would. I think it's kind of funny. The other day, my wife picked up some spices. You know, because we do a lot of cooking. We go through, and it was one of those, the big things of spices, and I'm not joking. It was the big thing of spices, and it was filled barely over the halfway point, unopened. And I said, couldn't you have gotten one that was more full? And she said, they all kind of look like that. I'm used to that, I'm used to it here. She bought a brand new thing of spices that was, I'd say maybe at most 60% full. And I couldn't help but thinking, am I getting ripped off here? So I waited, but it didn't help because it's the weight of the canister too. But I'm looking at that going, I can't imagine people are just going to happily buy that thing. So when you're buying your oranges and you get the one that's a half orange or one with a big bite out of it, or that's what it felt like. Somebody took a bite out of my stuff. Okay? Now, question.
So the 25.2 pi is the max error, and then that
Would be
is the relative error.
Maximum, yeah, it's always preceded by the word maximum because it is possible that I got lucky and there was actually no error. So the most I can be off is about 4 2/3 percent. That's what we're saying. Now, let me show you another way to do the same problem. You're going to like this. If the only question I had asked was max relative error. By the way, you had to calculate both because I asked you what is the maximum error. So you had to calculate the maximum error. And therefore, in order to calculate the maximum relative error, I needed both. One of the reasons why you like relative error, if the only question was relative error, then I would not have needed to do this calculation and this calculation. Not like they're exactly difficult, but I wouldn't have had to do both. I could have actually started the problem differently. And a lot of times you're only asked for relative error. And one of the reasons people like relative error better, more mistakes are going to be made on the units, believe it or not, than on the calculus. And because we're math people, if you're not a physics person, units, you never think units. But I need units. I'm asking a volume question because I could have asked for surface area, in which case it'd be squared. So if I just wanted to set up this problem independent of the actual values, I said we make cans. Let me change the problem, just so you understand. We make cans I gave you specific values. What if I changed it and I gave you the relative error? So if I gave you the relative error, what is the maximum relative error for R in this case? Wouldn't it be 0.1/6 times R? Everybody see that? I don't need to convert that to a percentage. That would be 1/60th. Okay? And DH would be what? 0.2/15H. I know that seems kind of silly, but that's I'd be saying that in general. Kind of like when I said the cubes, we were off by 1%. You could change that to 1 out of every 100, if that made it easier for you to think about. So if I'm just doing this, then what is dV? Well, that's this. And this is also sort of a built-in check, and then this is pi r squared h. Can I reduce this quotient? Yeah, sometimes we forget the obvious. When you're reducing and you have more than one term on top, don't factor. No, never factor, that takes too long. Pull it apart. That's the only way algebraically to do this correctly. Oh, I have this quotient, which is what? I's cancel, one of the r's cancels, the h's cancel. What am I left with? 2 dr over r. How about the second quotient? Well, the pi r squareds cancel, and I'm left with just dh over h. Does everyone see that? This is true. This is cans. This would always be true for cans. That the relative error is estimated by this quantity here. So now what if I gave you percent errors of the radius and the height instead? Could you not just stick them into that answer? Yeah. Yeah, that would be really easy to just go ahead and do the calculation. If I said we make cans of various sizes and our radius is off by as much as, give me a percent, and our heights are off by as much as, give me a percent, because we make little cans, we make big cans. Does that make sense? I told you how to do a problem with that specific sized can, and that's fine. But what if I could apply this to all cans that we make, like I did with the cubes? Didn't matter how big the cube was, our percent error was maximized with this value. Then that would be a lot easier, wouldn't it? Because now I just say, well, dr over r is the percent error in radius. dh over h is the percent error in height, and I could just do that calculation easily. Now, go back to the numbers that I used here. Oh, okay, what's dr over r? What's dr over r? Isn't that 0.1 over 6? And what's dh over h? Isn't that 0.2 over 15? And then when I do this calculation, I'm going to get the same answer we got here. That's always going to be true. Okay? You all with me on this? All right, let's do one more, but now we're going to do one that's slightly bigger. This will be the last one for the day. We're going to do a 3 independent variable problem. Yikes. Now, we have calculators. Would we actually estimate this if we had a calculator in our hand? No. No, but that's why I'm starting with a problem that's actually really low level on the big picture of what we're doing, so we can do our problem from beginning to end, and then we can check our answer using the calculator. Because this problem can get way bigger. Now, a lot of folks say, why would I do this stuff in general? Well, here's the issue in general, especially when we're talking about relative error. Let's go back to our example with the cube. Okay? I have a cube, and each edge and you say to little kids, inside voices. They're literally 2 feet apart. So anyway, yeah, sorry. If every measurement, I said, let me consider every possible value of the highs and the lows. So let me use an overly simplified example. I have cubes and they're supposed to be 100 centimeters in each direction. And the maximum error is 1 centimeter in each direction. It's still 1%. That means I could be as much as 99 to 101 for each dimension. Do you agree? Now, how many values are there between 99 and 101 centimeters? How many values are there? Infinitely many. Okay, so suppose I said, you know what, let me just do it incrementally because I'm going to use a computer. Let's just say I went every point 001. So I did 99, 99.001, 99.002, all the way up to 101. Now that's 2,000 different measurements. And I'm going to do that the same for all 3. That's 2,000 times 2,000 times 2,000. That's 8 billion independent calculations. And then what I do on the computer, I have it take the highest, I'd have it take the lowest, I'd find those differences, one's positive, one's negative, and then I'd simply average them together. And by the way, you're going to get exactly the same answer in the end. Now, I said, let me take an infinite number of values and just increment them every 1/1000th. I could make them more increments. So now you take something like this, and we do the same thing. I want to find the maximum error, relative error, and all these things. Technically, there's an infinite number of calculations. We pick a convenient value. I just gave you an overly simplified problem that had 8 billion calculations. You did the whole problem from beginning to end in a minute with one calculation, and in the end, your value is going to be within 1/10,000th of a percent of the actual value. Way more practical. But I still know how to do it. Yeah, one independent variable. What if there's more than one independent variable? What if there's several independent variables? What if I have sines and cosines and needed the x's and things? It turns out it's start being beyond the ability for technology. It's too many variables. You can't hold all variables constant at the same time. See, a partial derivative, you're holding everything constant except one, but you're doing it for each variable, and in the end, you're going to get a value that is so ridiculously close to the actual, if you had the ability to do the calculations. So I was doing this problem, and I was showing this in a graduate statistics class, and we had the multiple variables. And some knucklehead who didn't understand the math said, well, why don't we just do this? I said, well, because we did a problem, and the order of calculations required, if we just did what we said, every 1/1000th, it was on the order of 10 to the 23rd calculations. And then I'd have to figure out, have the computer sort them and find the high and the low. Because when you're doing pluses and minuses and transcendental functions, it's not as easy as just taking two extreme numbers. You actually couldn't. No human being could figure out what numbers to use. So when they said, well, just have the computer do it, and I laughed. I said, well, yeah, but it would be like 1,000 years before it was done calculating the problem that we did, and I showed them how to do it like in a minute. I said, that's why this is so valuable. I can do estimations that are absurdly close, ridiculously fast, when a computer might take a really long time because of the number of calculations required to go through and then pick the highs and the lows, and and you said, that's not good use of computer time if I know my estimations are absurdly close. My answer that I get as an estimate, is not going to be equal to the answer. But after you've seen a few examples, you realize how close it's going to be. So then when we're talking about maximum relative error, it's the same idea. It's going to be absurdly close to the answer, and for all practical purposes, it's what we're going to use, because anything else would take us so long. All right, so let's figure out happy point, HP. How's that? Happy point is 1, 3, 4. So dx is, what am I here? What's dx?
Negative 0.01.
dy
0.02.
and dz?
0.03.
Okay, good. If I get those incorrect, I can have flawless calculus, but I will get the wrong answer because I actually did a different question. So I gotta get those right, okay? Let's go ahead and just start off, get it out of the way. Let's calculate f of 1, 3, 4, because that's my starting point. My final answer to the problem, I don't expect to be very far from this number. Do you agree? Right, we're going to move a little bit, but not a huge amount. So I want to get this one right. So tell me when you got a number.
-11.
-11? Okay. So my final answer, I don't expect to be very far from that. Okay? So I can say with certainty, well, let's go ahead and do our dz. So delta z is going to be estimated by I'm sorry, not z, sorry. W. Z is one of my variables now. So that's going to be the partial with respect to x dx plus, or actually, sorry, I'm getting ahead of myself. The partial with respect to x evaluated at 1, 3, 4. This is not a function, this is a scalar. I have to take the derivative and evaluate it. So this is one of those times, don't leave things in function form and then multiply those out. It gets too messy. You find the derivative and immediately evaluate it because that's what you're going to use for your final answer. dx plus fy of 1, 3, 4 dy plus fz of 1, 3, 4 dz. Okay? So, over off to the side, what is fx? Let's do that first. partial with respect to x is.
8xz minus 3y squared.
With respect to x is 8xe minus 3y squared. So what is the partial with evaluated at 1, 3, 4? I usually do it in this order, just get out of the way. So we are 32 minus 27, that's 5. All right, partial with respect to y. So negative 6xy. Now evaluated at 1, 3, 4.
Negative 18.
Negative 18. And finally, the partial with respect to z,
4x squared.
4x squared. So that evaluated at 1, 3, 4. Well, that makes it kind of easy. It's just going to be a 4. All right, we are ready. We've done everything necessary. So now I can say that f of 0.99, 3.02, 4.03 is equal to f of 1, 3, 4 plus delta z, but that's estimated by negative 11 plus 5 times negative 0.01 plus negative 18 times 0.02 plus 4 times 0.03. Okay, let's calculate that bad boy. Tell me when you got a value.
Negative 11.19.
11.29.
29.
Did you say 29?
He said, well, I said 29.
I got 29. Did you get it?
I got 19 also, yeah.
Did anybody else do it? See, we're on the same wavelength. Anybody else? 19 or 29? 29, okay. Yeah, I think it's probably, okay. So in simple English, well, the final answer is always state the estimation. Because sometimes it's not always clear because I got this big long row here. Now you never have to show the check. I'll usually put it on the key, I'll put the check, but here's our check. What's the actual value? I'm gonna put it underneath. What's the actual value? This is how I know that I did a good job. I'm hoping I get a number really close to that. All right, anybody get a number? Actually, you don't have to give me the approximate. It's exactly. It's a terminating decimal. So what? I'll put it up here. The exact value of this is equal to negative 11.288376. So our error is just a tiny bit over 0.01. You agree? Or another way of saying it, our error is less than 1/10,000th. So our error is less than 1/100th%. I'd say that's pretty good. Okay, it doesn't mean, wow, we're incredible people. No, it means I feel really good about my answer. That's why. And again, going back to the original problem, these changes are small relative to these values. So we didn't expect the final answer to be off by a lot. Agreed? Okay, everybody cool? All right, that's differentials. That's what they are. And It's just a beautifully simple use of what we're doing to do certain types of estimation problems. And in real life, I always remind people, in real life, there are very few equals. How many have had at least Math 119? Stats. In stats, by the way, nothing is equal. Everything's an estimation. You're taking samples to make conclusions about a population. The value that you calculated for your sample, that's called a statistic, you're using to estimate, not calculate, the value of the parameter, which is the population. That's the whole point of statistics. And if you take good samples, your statistic ought to be really close, a good representation of the parameter, but you can't ever know the parameter. You know, I want to talk about, you know, the size of water molecules in the ocean. Probably can't take all the water molecules in the ocean. That might take me a couple days, right? Probably take a sample of water from the ocean. I want to talk about, you know, average height of human beings. Probably can't measure everybody because there's a lot of human beings, you know. You take samples. So nothing is equal, but the larger your sample, the closer it gets. In fact, there's a limit. In other statistics become parameters based on a limit. And most things are finite, but it's sort of like the limit as n goes to infinity, you know. But nothing's ever equal. Everything's an estimation. Everything. And then now you get to real life and you realize, and in those in linear algebra, you understand this. Very few equals, most things are actually inequalities, right? Like I said, when you go to the grocery store and you have $20 in your pocket, the only rule is you can't exceed $20 when you get to the check stand. But do you have to spend exactly $20? No, 20 or less. And on and on and on. Everything's really an inequality. Very few things are actually ever equals. So whether I'm doing a calculation or an estimation, so we want to understand the mathematics of estimation. It's the bigger topic is asymptotic convergence. I always say go back to Taylor's series. Remember what the whole point of that was. We had ways of doing calculations that we couldn't have done. If you're in my class, my favorite problem was to do the integral that can't be done. There's an infinite number of definite integrals that cannot be evaluated because they have no antiderivative. So we use Taylor's series to do estimations. But if you were in my class, I showed you our crude estimations were often accurate to, you know, more than 10 decimal places with like 3 or 4 terms because I'd use Desmos to show the decimal. Like, my God, we just did this problem in a couple of minutes. We took a problem that cannot be done, and we got an answer that was more accurate than anything we'd ever actually needed in real life by integrating a simple polynomial rather than some nasty function that had no antiderivative. That's where estimation is very powerful, asymptotic convergence. And I don't actually have to take a limit. I just need a few terms if I do the problem correctly. That's the power. Now, we're not doing any of that in this class. We're doing something way simpler than that, just to kind of give you a reminder, because this is something you might use in an engineering class way down the road. I don't know that you do any of this in a physics class. In an engineering class, yes. Yeah, because I've talked to engineering instructors. They said stuff like, you know, being able to do estimations of problems with lots of variables is really important because you can't actually do the calculations directly all the time. It's too much. All right, let me go ahead and stop this.